When should I use /dev/shm/ and when should I use /tmp/? When should I use /dev/shm/ and when should I use /tmp/? Can I always rely on them both being there on Unix?
/dev/shm is a temporary file storage file system, i.e., TMPFS, that uses RAM for the backing store. It can function as a shared memory implementation that facilitates IPC. From Wikipedia. Recent 2.6 Linux kernel builds have started to offer /dev/shm as shared memory in the form of a RAM disk, more specifically as a world-writable directory that is stored in memory with a defined limit in /etc/default/tmpfs. /dev/shm support is completely optional within the kernel config file. It is included by default in both Fedora and Ubuntu distributions, where it is most extensively used by the PulseUdio application. Emphasis added. /tmp is the location for temporary files as defined in the File System Hierarchy Standard, which is followed by almost all Unix and Linux distributions. Since RAM is significantly faster than disk storage, you can use /dev/shm instead of /tmp for the performance boost, if your process is I/O intensive and extensively uses temporary files. To answer your questions, no, you cannot always rely on /dev/shm being present, certainly not on machines strapped for memory. You should use /tmp unless you have a very good reason for using /dev/shm. Remember that /tmp can be part of the file system instead of a separate mount, and hence can grow as required. The size of /dev/shm is limited by excess RAM on the system, and hence you're more likely to run out of space on this file system.
In descending order of TMPFS likelihood. Since you are asking about a Linux-specific TMPFS mount point versus a portably defined directory, that may be TMPFS, depending on your sysadmin, and what's default for your distro, your question has two aspects, which other answers have emphasized differently. Appropriate use of various TMP directories, appropriate use of TMPFS. Appropriate use of various TMP directories. Based on the ancient file system hierarchy standard, and what systemd says about the matter. When in doubt, use /tmp, use /var/tmp for data that should persist across reboots, use /var/tmp for large data that may not easily fit in RAM, assuming that /var/tmp has more available space, usually a fair assumption. Use /dev/shm only as a side effect of calling shm_open. The intended audience is bounded buffers that are endlessly overwritten. So this is for long-lived files whose content is volatile and not terribly large. Definitely don't use /dev/shm for executables of any kind, as it's commonly mounted no exec. If still in doubt, provide a way for the user to override. For the least amount of surprise, do lighten temp and honor the tempdir environment variable. Where TMPFS excels. TMPFS performance is deceptive. You will find workloads that are faster on TMPFS, and this is not because RAM is faster than disk. All file systems are cached in RAM, the page cache. Rather, it is a sign that the workload is doing something that defeats the page cache. And of the worst things a process can do in this regard is syncing to disk way more often than necessary. Sync is a no-op on TMPFS. This syscall tells the OS to flush its page cache for a file, all the way down to flushing the write cache of the relevant storage device, all while blocking the program that issued it from making any progress at all, a very crude write barrier. It is a necessary tool in the box only because storage protocols aren't made with transactions in mind. And the caching is there in the first place to make it possible for programs to perform millions of small writes to a file without noticing how slow it actually is to write to a storage device. All actual writing happens asynchronously, or until sync is called, which is the only place where write performance is directly felt by the program. So if you find yourself using TMPFS or EAT just to defeat sync, then you, or some other developer in the chain, are doing something wrong. It means that the transactions toward the storage device are unnecessarily fine-grained for your purpose. You are clearly willing to skip some save points for performance, as you have now gone to the extreme of sabotaging them all. Seldom the best compromise. Also, it is here in transaction performance land where some of the greatest benefits of having an SSD are. Any SSD worth its salt is going to perform out of this world compared to what a spinning disk can possibly take. 7,200 revolutions per minute equals 120 Hz, if nothing else is accessing it. Flash memory cards also vary widely on this metric. It is a trade-off with sequential performance, and the SD card class rating only considers the latter. So beware, developers with blazing fast SSDs, not to force your users into this use case. Wanna hear a ridiculous story? My first sync lesson, I had a job that involved routinely upgrading a bunch of SQLite databases, kept as test cases, to an ever-changing current format. The upgrade framework would run a bunch of scripts, making at least one transaction each, to upgrade one database. Of course, I upgraded my databases in parallel, 8 in parallel, since I was blessed with a mighty 8-core CPU. But as I found out, there was no parallelization speedup whatsoever, rather a slight hit, because the process was entirely I/O bound. Hilariously, wrapping the upgrade framework in a script that copied each database to /dev/shm, upgraded it there, and copied it back to disk was like 100 times faster, still with 8 in parallel. As a bonus, the PC was usable too, while upgrading databases. Where TMPFS is appropriate. The appropriate use of TMPFS is to avoid unnecessary writing of volatile data, effectively disabling writeback, like setting to infinity on a regular file system. This has very little to do with performance, and failing this is a much smaller concern than abusing sync. The writeback timeout determines how lazily the disk content is updated after the PageCake content, and the default of 5 seconds is a long time for a computer. An application can overwrite a file as frequently as it wants in PageCake, but the content on disk is only updated about once every 5 seconds. Unless the application forces it through with sync, that is. Think about how many times an application can output a small file in this time, and you see why syncing every single one would be a much bigger problem. What TMPFS cannot help you with. Read performance. If your data is hot, which it better be if you consider keeping it in TMPFS, you will hit the PageCake anyway. The difference is when not hitting the PageCake. If this is the case, go to where TMPFS sucks, below. Short-lived files. These can live their entire lives in the PageCake, as dirty pages, before ever being written out. Unless you force it with sync, of course. Where TMPFS sucks. Keeping cold data. You might be tempted to think that serving files out of swap is just as efficient as a normal file system, but there are a couple of reasons why it isn't. The simplest reason: there is nothing that contemporary storage devices, be it hard disk or flash-based, loves more than reading fairly sequential files neatly organized by a proper file system. Swapping in 4 KB blocks is unlikely to improve on that. The hidden cost: swapping out. TMPFS pages are dirty. They need to be written somewhere, to swap, to be evicted from PageCake, as opposed to file-back clean pages that can be dropped instantly. This is an extra write penalty on everything else that competes for memory, affects something else at a different time than the use of those TMPFS pages.
Okay, here's the reality. Both TMPFS and a normal file system are a memory cache over disk. The TMPFS uses memory and swap space as its backing store. A file system uses a specific area of disk. Neither is limited in the size the file system can be. It is quite possible to have a 200 GB TMPFS on a machine with less than a GB of RAM if you have enough swap space. The difference is in when data is written to the disk. For a TMPFS, the data is written only when memory gets too full or the data unlikely to be used soon. Although most normal Linux file systems are designed to always have a more or less consistent set of data on the disk, so if the user pulls the plug they don't lose everything. Personally, I'm used to having operating systems that don't crash and up systems, e.g., laptop batteries, so I think the X2/3 file systems are too paranoid with their 5 to 10 seconds checkpoint interval. The X4 file system is better with a 10-minute checkpoint, except it treats user data as second class and doesn't protect it. X3 is the same, but you don't notice it because of the 5 seconds checkpoint. This frequent checkpointing means that unnecessary data is being continually written to disk, even for /TMP. So the result is you need to create swap space as big as you need your /TMP to be, even if you have to create a swap file, and use that space to mount a TMPFS of the required size onto /TMP. Never use /dev/shm. Unless you're using it for very small, probably mapped, IPC files and you are sure that it exists, it's not a standard, and the machine has more than enough memory plus swap available.
Use /TMP/ for temporary files. Use /dev/shm/ when you want shared memory, interprocess communication through files. You can rely on /TMP/ being there, but /dev/shm/ is a relatively recent Linux-only thing.